All right, welcome to the second module of this short course on machine learning in communications. We are going to look at statistical estimation and its role in machine learning in this module, both lectures 3 and 4. In this specific lecture, I'm going to cover some basics of statistical estimation for those of you who have not been exposed to them yet. Then we are going to use that knowledge to interpret least square regression as maximum likelihood estimator. Then we are going to interpret the regularized linear regression as a map estimator. And we are then going to conclude this lecture with an interesting idea of basis expansion or feature augmentation, because of which linear regression is actually a little bit more general than you might first think, especially when you hear about linear. You might just associate that with the linear functions, but that's not really the case. You can augment your features to also learn polynomial functions using exactly the same process. So we'll see what I mean by that when we reach there. So let's start with a simple coin toss example, which will remain with us. So I'll sort of introduce the basic ideas using this example. Let's consider a biased coin, which has a probability of heads equal to theta star. Theta star is unknown to you. Let's say you toss this coin n times and get a specific sequence of heads and tails, right? So let's say you get heads, tails, tails, followed by heads, and so on. Let the fraction of heads in this sequence be theta hat. Okay. Now the question, a natural question to ask, right, at this point is, can theta hat be very different from the true theta star, right? Because ultimately theta star is unknown to us, but we would like to infer something about it using the sequence that we are getting. Now, a short answer to this is, sure, it is possible that theta hat can be very different from theta star, but it is not probable if n is large, right? It is possible, sure, but it is not probable if n is large, right? Now, this statement can be formalized using Hoeffding's inequality, right? You could bound this probability, which is probability that theta hat, right? Think of this as the estimate, right? I haven't really introduced the estimate yet, but think of this as estimate of this true theta star, right? Something that you're estimating given data. Probability that this estimate is outside some epsilon neighborhood of the true theta star can be upper bounded by a term that is a decaying exponential with n, right? So it is e raised to power minus n term here, which means that this probability, right, is going to be very small when n is large, right? So this has some interesting implications, right? This shows that one can actually learn, right, unknown theta star, and people call it out of sample theta star as well, because you don't actually know this. This is not something that is contained in your data, which is in this case a sequence. And you can learn that from in sample theta hat, something that you are observing, right? Therefore, endowing a distribution on the data set is necessary to ensure generalization to unseen data, right? We touched upon this very briefly on the first day as well, right? Why endowing distributions is important, or why making some assumptions about the mappings is important, right? Otherwise, the learning problem becomes hopelessly difficult. So in order to ensure generalization, right, we sort of are assuming that there is some distribution endowed to the data set. Now, one can start asking these type of questions, right, and sort of formalize this notion a lot more using the idea of probably approximately correct learning, which is part of computational learning theory. When I was preparing for this course, I thought I might also cover some part of it, but at the end of the day, I realized I just don't have sufficient time. It was either this or some of the case studies that I introduced, because it's sort of for the communications audience, I wanted to introduce those case studies as well. But for those of you who are interested, the fourth reference that I provided on in the first lecture is an excellent reference to read more about this topic. Okay, but we won't really be needing these ideas throughout the course. So this is sort of for more for your insight, for intuition, why we care about distributions. All right. So let's revisit our statistical setting, right? We have input features X, labels Y, right? That was the setting we have had since our first lecture. And we are assuming that your features X, Y, right? Features X and output Y, which is written as XY here. It is sampled from a joint distribution PXY. Okay, so PXY. And it would be a PMF if we have a discrete case, it will be a PDF if it is a continuous case, right? So it'll be using the same notation here. And we also assume that these data samples that you are getting from this distribution are sampled IID, independent and identically distributed. You'll see that this assumption will be necessary when we start writing our likelihood functions in a couple of slides. Okay, so this reduces now the learning problem to learning or estimating the parameters of this unknown distribution. We'll see, right? And not surprisingly now, estimation theory is going to play a role in this development, which is basically the main topic of this lecture. So this is where we start connecting the learning problem to the sort of the estimation problem. Right, so whenever we start discussing the estimators, right, so one of the first things we need to cover quickly is the Bayes rule. I'm pretty sure everybody here has seen that in one form or another. So let me just introduce all the terms, but introduce them in the context of data, right, just so that we gain some intuition as to what each term represents. So we have two random variables, xy, joint distribution, pxy. So Bayes rule connects probability of y given x with probability of x given y, right, in terms of probability of x given y and the marginals. So let's look at each term separately. So p of y given x, the term we have on the left here, right, is the knowledge of the outputs after the data has been revealed to you, right? So after the input is revealed, right, what can you learn about the output from that input? That is probability of y given x. We call it a posterior. And when we come to the map estimator, this is what we will be maximizing. Okay. Now, P of y, right, the marginal of y, this represents the belief about the outputs before the data is revealed to you, right? For example, if you are tossing a coin, if you have some knowledge, some prior knowledge about the behavior of that coin, that will go into the prior PY. And this often comes from domain knowledge. So this is a prior, it will be useful in our map setting. Now you have this term P of x given y. This is what we call a likelihood term, P of x given y. This is the likelihood of observing a specific value of input for a given value of the output. Let's say it was revealed to you that your output is y equals to I, right? What is now the probability that this output was generated by, say, x equals to j, right? So this gives probability of x equals to j given y equals to I. That is the likelihood term. And this is the term we'll be maximizing when we look at the maximum likelihood estimators. Now, the term in the denominator on the right-hand side, P of x, is just the normalization term. It won't really play any active role in any of the development that we are discussing, right? So you can sort of safely ignore that for now. In statistical estimation, right, we often look at two types of estimators: the maximum likelihood estimator, which is the frequentist approach, and map estimator or Bayesian estimator, right, which is the Bayesian approach. We are going to look at both of them. I'm going to describe the basic ideas over the next few minutes using a simple coin toss example that we just introduced a couple of slides back. But remember, eventually what we are interested in here is probability of y given x. Okay, it will be clear why this is the quantity of interest if it isn't already from some of the examples we are doing later. But these basic ideas will be introduced just using the simple example. Okay, meaning I may not go into the conditioning right away, we are just going to look at the data sets generated by this simple example. Okay. So let's say that we toss a coin a few times, observe a given data set, right? So let's say we toss this coin 6 times, and we receive, say, TH, TH, TT. Right? Now think of this as your data set. Now, this qualifies as a data set. Our goal is to estimate the underlying distribution. Okay. Now so the first step is to set up the problem, which means we have to make some reasonable observations here. So let's say we assume that the tosses are independent and the outcome is binary, very reasonable observations, right, for this experiment. Now, this means that each coin toss can be thought of as an outcome of a Bernoulli trial, right? So yi is sampled from Bernoulli with parameter theta. Now, the moment you make that assumption, that becomes your hypothesis class or model class, right? I just wanted to sort of make that connection with what we discussed last time as well, right? So this becomes your model class. This is the class within which we will be searching. Okay. Now, from this model class, our objective is to find theta hat, right? Our estimate of the true distribution theta star, right? Now this estimation part is where ML and map start coming into the picture. Let's very quickly look at what maximum likelihood estimation is, right? The question that we try to answer in ML estimation is, are there any specific values of theta that make our data set more Y more likely? Okay? So before I go into this in more detail, make sure that you understand the difference between this Y, which is some generic data set. It has nothing to do with the output, right? For these couple of examples I am giving, this is just some data set. And we are introducing the basic notions of estimation in terms of this data set, but this is not really the output Y that we defined before, right? So I'm not sure if you can see the distinction between the font type that is used here, but it is different. Okay, so now maximum likelihood, as I said before, right, is nothing but you take your likelihood function, which is probability Y given theta in this case. Theta is the parameter that you are estimating, and then you just try to maximize that likelihood function. Okay, and the value of theta that maximizes the likelihood function is your estimate, or the ML estimate, which will be represented as theta hat of ML. Right. Now, also note that when we work with this likelihood function, the IID assumption that we made before will be very helpful, right? Because this is now the probability over the whole data set, but we know that each example in our data set is sort of sampled IID from the underlying distribution. So which means that you can write this joint distribution as a product. Product of the individual terms, which will be very useful for writing our estimator. Now let's look at this ML estimate for this coin toss example that we already gave. The likelihood function for this example is actually quite straightforward. Let's say that you have NH number of heads in this sequence and T number of tails in this sequence. So if you write the probability, right, P of Y given theta for this data set, it is nothing but theta times 1 minus theta and so on, right? So you have NH theta terms and NT 1 minus theta terms. When you combine, this is the expression that you get, right? So where NH again is the number of heads and NT is the number of tails, with N being the total number of samples you have in the data set. Now, once you write the likelihood, right, you can either maximize that directly, or you can take the logarithm of that likelihood and maximize that. It doesn't matter, these are equivalent since log is a monotonically increasing function. So if in this case, it turns out that the log likelihood, maximizing over log likelihood is easier, you take the log, right, of L theta and try to maximize, and the ML estimate that you get for this example is actually quite intuitive. So theta ML, which is the ML estimate, is nothing but NH, number of heads in the sequence, divided by the total number of samples in the sequence, right? So very intuitive estimate. Now, you might say that, sure, this sort of intuitively makes sense, but then one useful thing to know, and I'm sure many of you might already know this, is that ML is actually optimal in some sense, right? It is optimal in the sense of minimizing KL divergence. So let me show that through a very quick example before we proceed. I think this will be useful, especially if you haven't come across this result yet. Okay. So this is where I add a new page. All right. So we are looking at the optimality of this ML estimation, right? So let's consider a discrete random variable y. Right? We have a, let's see, y, discrete random variable, right? Which can take values from this discrete set, 1, 2, 3, so on up to k. This idea is more general, but it will be very straightforward to demonstrate for this simple example. Now, the log likelihood, right? Log likelihood for this can be written as log likelihood of theta, let's say, is 1 over n, I equals to 1 to n, log of probability of yi given theta, right? So now I can combine the similar terms, right? So you have this sample of size n, and some of those sample values are going to be 1, the others are going to be 2, and so on. So I can combine those terms here in the following way: 1 over n, j equals to 1 to k, and j, which is the number of times the jth element appears, and then you get log probability y j given theta. Right, so nj here again, nj is the number of j in the data set, a number of times j appears in the data set. Right, if we had infinite data, right, so we can say that limit n tending to infinity nj over n is nothing but probability y equals to j under the true model. So this sort of conditioning on theta star should be read as under the true model, right? And this is nothing but p star of j. So we just define this as p star of j as a shorthand notation. Okay, so similarly, I can define p theta of j, which is the same probability y taking j, right, under our assumed model theta. Okay, so we have now two terms here, p star of j and p theta of j, right? So think of theta as just any parameter or parameters which are defining your distribution. Okay, so let's look at the likelihood now, log likelihood, under this assumption that n tends to infinity. Okay, so we are looking at log likelihood again, limit n tends to infinity, 1 over n, log likelihood of theta. It's nothing but j equals to 1 to k. I'm absorbing this 1 over n term with nj to write that as p star j, p star of j, and log of p theta j. Right, then within log, what I do is I multiply and divide by p star. Right, and then I just write this log a b as log of a plus log of b in the following way. So I just j equals to 1 to k, p star j, log of p star j minus j equals to 1 to k, p star j, log of P star j divided by P theta of j, right? So pretty straightforward manipulation of this expression. Now, what is interesting is what these two terms represent. So this first term is nothing but the negative of entropy, right? And the second term here is just the KL divergence, right? Now, if you sort of maximize your log likelihood, right? Let's write the maximization problem, argmax of theta 1 over n, log likelihood of theta. This is nothing but, so since the first term, which is just the entropy, doesn't contain theta, right? So we are not, this term is not going to impact our maximization problem. This can now just be written as argmin over theta KL divergence between the true distribution and the distribution that you assume. Okay. Now, what does it mean in terms of the model classes and so on that we introduced last time, or the hypothesis class? So if this is your model class or hypothesis class, right? And let's say that theta star, right, the true distribution is not contained, or truth is not contained in the model class, then what you're trying to do is within the model class, right, you're coming up with theta hat. Let's call it theta hat ML, and this will be such that the KL divergence between the two distributions is minimized, right? That's sort of what maximum likelihood is trying to do. Okay? Now, one of the reasons I went through this is to go over an interesting point, to just put some of the machine learning algorithms and the complexity into context. So there is this idea of error decomposition in ML. In machine learning, we make a lot of different types of errors, right? One error is something that we just discussed, where you choose a model class which doesn't contain the truth, right? Then you're learning within that model class, and you're making some modeling error, right? So I'm just representing that as a modeling error. Now think of this as some theta star, right? Some truth, reality. Now, if you paid attention to the previous example we just discussed, I actually made an assumption that we have infinite data and tending to infinity, right? In reality, we won't have that, which means that we are not going to approach that true estimate value. There is going to be some estimation error, right? Which is going to push us even from this sort of optimal point, it's going to push us somewhere else because we have limited data. Now, even finding this may not be always possible, because you are eventually solving an optimization problem. So what if your function is, say, non-convex, right? Or your optimization problem is NP hard. So you may have to come up with heuristics, and hence you introduce some optimization error. And hence this is what you eventually get, which is your estimate, which can be pretty far away from reality because of multiple choices you made on the way. You can actually see quite easily now that you can trade one of these errors for the others. For example, if your hypothesis class is smaller, you might be able to shrink the estimation and optimization errors, right? But in that case, your modeling error might be large. So at the end of the day, it is a pretty difficult choice in most cases. And the problem is, for more difficult learning architectures, we cannot always find out, right, which of these errors is dominating, right? But just keeping this picture in mind when you are working with difficult learning architectures, I think is useful. So you need to always keep in mind there are many different types of errors you are making. So you have to make sure how sort of they are being balanced. Okay. So let's move forward now and introduce the second estimator, which is the map estimator, maximum a posteriori probability estimator. So the general idea of a Bayesian is to treat theta, right, the parameter that we are interested in learning. I'm again going back to the coin toss example, as a random variable instead of being deterministic. Right? If you remember, we did not treat theta as a random variable in the frequentist approach that we just discussed. So here we are going to treat theta as a random variable, which is where the prior will come into the picture. Right now, from the Bayes rule, we know how to write probability of theta given our data set. Again, I'll remind you why here is not an output, right? It is your data set. Theta is the parameter you're learning. So you can write the posterior where p theta is your belief in theta. We'll see how to select that. And an interesting connection that we'll learn very soon is that this prior will actually have, or the choice of prior will have some connections to regularization in machine learning, right? Or the idea of regularization in machine learning. So if you have learned machine learning more from the algorithmic perspective, I think you will find this connection useful. Okay. Now, the specific estimator or map estimator that we are interested in is theta hat map, which is just maximizing this posterior p of theta conditioned on y, right? So argmax of this is the specific estimator we are interested in. Okay, so at this point, you might ask, right, how do we choose priors? So in order to do that, there is this concept of conjugate priors, which is very useful because if you pick up some prior arbitrarily, right, your problem may not remain tractable. So here you have to sort of balance tractability and realism. And one thing that people often do is to select a prior distribution such that when it multiplies with the likelihood, the posterior has the same form, right, or the same distribution as the prior. Right? The example that will be useful for to illuminate this and is also useful for what we are studying, right, is the beta prior, right, for the Bernoulli likelihood. So we had the Bernoulli likelihood in our coin toss example, and now if you choose beta prior, we'll see that things will just fall in place, as I'll show in the next slide. So first of all, the form of beta prior is the following. P of theta, right? Remember theta here, you can think of that as a sort of probability of heads. 1 minus theta is probability of tails, right? So that term is coming here, raised to the power some mh minus 1, which is a hyperparameter that you can select. And I'll interpret this specifically in a moment. 1 minus theta is sort of probability corresponding to the tail. So this is that term raised to the power mt minus 1. And mt is a hyperparameter that I'll associate with the outcome of tails in a minute. Okay. Okay, so this is your beta distribution, right? Now let's see if we use this beta prior, right? What type of posterior do we get? Okay. So theta map, right, which is our map estimator. This is just maximizing the posterior p of theta given y. And from Bayes rule, that is nothing but this expression here. Okay, so I have just colored this just for you to see it quickly, right, which term corresponds to which. So this is your likelihood here, and this is your prior. You can see that the form is such that you can easily combine these terms and you get beta for your posterior as well. Okay. Another thing that is interesting to note, and the reason why I did not dwell too much on the prior in the previous slide is the following. You see that MH here is adding with NH and MT is adding with NT. So you can actually interpret MH and MT as sort of the pseudo counts, right, that were somehow known to you. Let's say that you use the same point for sort of an experiment before, right? So you had some memory or prior. So this is really where, for example, domain-specific knowledge could be helpful, right? So these can be interpreted as some pseudo counts. Now, since the map estimator, right, by definition is doing nothing but finding the mode of the posterior, right? So posterior is beta, so its mode is very well known. So you get your map estimate, which is given by this expression here, right? Now, if you had infinite data, right, and you can check this very quickly, then this map estimate will approach the ML estimate because priors would not matter once your data set is extremely large, right? So the importance of priors will keep on going down and down. Okay, so nothing really special about this specific form of the map, right? I just wanted to show a couple of examples so that people know what we are talking about. All right, so how do we generalize this to the non-binary case? It is actually quite straightforward. Let's look at the setup. Let's say that your random variable x is no longer binary, right? So let's say it can take k values, and probability that your random variable x takes a value j is theta j. Then you can define your parameter vector, right? A vector of parameters as this theta 1, theta 2, so on up to theta k. Obviously, they all sum to 1, right? Now, similar to the binary case, our objective here is to estimate theta hat. It's just that theta is a vector in this case. So if we are doing maximum likelihood, right, we write the likelihood function, which in this case is, again, quite straightforward to write. It has the same form pretty much. If you think about, say, theta 1 as theta and theta 2 as 1 minus theta in your k equals to 2, the binary case that we have discussed before, right? So exactly the same form. Now, if you want to do map estimation in this case, right, you again need to choose a prior, right? So here, the prior that is often chosen in this case is the Dirichlet distribution, which is the generalization of the beta distribution. You can even see that from the form here. You have theta j raised to the power mj minus 1, right? So, and we had similar, exactly the same, pretty much the same form in the binary case where we had theta raised to power mh minus 1, 1 minus theta raised to the power mt minus 1. You can treat theta as theta 1 and 1 minus theta as theta 2, right? So it's straightforward to sort of recover k equals to 2k's from this expression. Now, the map estimate in this case is also exactly, it also has exactly the same form, right? So we had this nj plus mj minus 1 form, and then you have a very similar term in the denominator. If you want to recover the ML estimate from this case, you can do one of the two things. One is you can take the limit that your data size goes to infinity, right? That you have a large data set, so that the importance of prior keeps on going down. The second thing you can do is to use a uniform prior, which in this case is just ML equals to 1. You can put ML equals to 1 and check for yourself that you will reduce to this intuitive ML estimate, which says that theta ML, right, which is the for j, which is the probability that your random variable is taking value j, is nothing but number of times it occurs in the data set divided by the size of the data set, right? Pretty intuitive. So let's quickly move on to the continuous case, right? Just pretty much for completeness, because we'll be using that very soon. So here, as opposed to the discrete case, right, where we were using a coin toss or Bernoulli, we will be using the Gaussian as an example. So here we have, again, data set y. Again, I'll remind you, don't think of this y as output yet, right? It's just some data set that is given to you, some values, y1, y2, so on up to yn. And we are going to model yi as a Gaussian, okay? So which means that probability of y, or PDF of y rather, has this form. And we are now mu and sigma squared, right? They become our model parameters. Mu and sigma squared are our model parameters in the same way as theta was the model parameter before. I'm not going to work this out for you, but this is a good exercise for those of you who have not gone through the estimation theory courses yet, to actually derive the ML estimates in this case. Fairly straightforward to do. And one can show that the ML estimate for the mean is nothing but the sample mean, and the ML estimate for the variance is just the unadjusted sample variance. Okay. Now, what happens in the map case, right? So if we apply a map estimator in this case, right, we will have to treat whatever we are estimating, right, as a random variable, as we discussed before, and then we will be maximizing the posterior. So what we'll be doing, even in the later machine learning examples we are going to cover, is to just focus on the mean mu, and we'll just treat that their sigma squared is some unknown constant. We'll see why I made that statement. So we are just going to focus on the mean. That is more important to us. So the conjugate prior in this case is just Gaussian. So you assume that mu is Gaussian distributed with some mean mu naught and variance sigma naught squared, right? So the PDF of mu under this assumed model is given here. And again, you can work out the math, and the map estimator that you'll get for this case is given here. Okay, as I said before, a good exercise for our younger colleagues to sort of learn these basics. Now, okay, so now why did I introduce all this, right? Let's start connecting this to machine learning through some basic examples. Let's consider linear regression, okay? So linear regression, what we assume here is you have, again, x1, x2, so on up to xb features, right? That is your feature set. And we assume, again, this is an assumption, we assume that you have a linear relationship between the inputs and the, or features and the output. Okay, so this is our assumption. This may or may not be true, right? But this is the assumption that we are making. So this is where we are selecting a hypothesis class. All right. So now if you expand this linear function, right, this is what you get. And these beta i's or beta j's are the weights. And we call these learning parameters. Beta naught, as we discussed very briefly also in the context of a neural network, is a bias feature. So you can also write this in terms of the vector notation, right? So this, let's just use the notation which I think will appear more. Beta transpose x and equivalently x transpose beta as well. So here I have just redefined some, you can just go over this slide if you want, but I've just absorbed this one corresponding to the bias feature in the notation of x as well, and used a slightly different font for this expanded vector, right? D+1 dimensional vector. Okay. So what exactly does linear regression do, right? So here we have data, right? Let's say these red points correspond to your data points, and we are just fitting a linear function that describes this data. So here, when we do that, and we discussed before as well, you may not always have a deterministic relationship between the output and input, right? So there is often, or I should say, almost always you're going to make errors, which are these bars here, right? Sometimes you make smaller errors, sometimes you make larger error. And that error is nothing but yi minus yi hat. Yi is the true value, y hat I is the estimated value. Okay. So now linear regression tries to minimize the cumulative error across all the training points, right? So we will have to formalize this by defining a loss function, which I'm going to do on the next slide. We are going to use a loss function, which we have already defined before, which is the squared loss. Okay. So this is the squared loss. By the way, this is just the cumulative loss, right? So this should not be confused with the likelihood function. We are going to make some connection soon, but this is just the cumulative loss over my data set, right? So that is nothing but I look at the error for one data point, square that, add that, and just take the average, right? And that can also be written in terms of the vector form as x transpose beta, right? Which is your y hat. Now this is a convex function in beta, right? So your learning objective reduces to the following. We are interested in finding an estimate for this vector beta, right? That minimizes this cumulative loss. Okay, so we are interested in minimizing this function here. Now, this can be done in one of the two ways. This is just a very straightforward case for which even a closed form solution for beta exists. That's called the normal equation. But you can also do this algorithmically using gradient descent algorithm, right? Now, if you're very new to machine learning, this would be a very good exercise for you to do how to write gradient descent for this very simple example. So you'll sort of go through some of the algorithmic choices that you have to make. Okay. Now, what I am more interested in this lecture, right, because we are taking this statistical viewpoint, is why, when does this squared loss make sense, right? I have made this choice, but I haven't told you when this makes sense, right? So let's look at this carefully, and this is where I am going to make some connections with the estimators that we have introduced already. Okay, let's consider a generative model, right? So let's assume that your features are sampled from an arbitrary distribution, right? We are not assuming anything about that distribution. And then you assume the following model for your output. And this notation will be useful to keep in mind. Y is beta transpose X plus a Gaussian noise term. Right, so again, a shorthand notation, there is a random variable sitting here which follows Gaussian, but I think you get the point. So I will be writing this. So this is often actually expressed as a shorthand as Y, right? If you know X, you can just say that this is Gaussian beta transpose X sigma squared, right? Which is what I have written here. And I'll be using this extensively in this and the next lecture. So the model parameters, right, for this generative model are beta and sigma square, right? So you can also now start thinking about this, right? We have, of course, seen these type of models many times in communication. So I won't dwell on that part much. So we are going to assume that sigma squared is an unknown constant, right? It is constant. We don't really care about what its value is. And let's now determine the maximum likelihood estimate for beta. Right now, the problem is very well defined. We have a probability model, right? We know what we are estimating, and we can define maximum likelihood problem for this. Okay, let's do that quickly. Now, in order to do this, right, we have to write the likelihood function or equivalently log likelihood, which in this case is given by this term, right? After making that IID assumption, right, you get log of product, which is written as sum of log here. And then this term under the model that we have chosen, right, this is nothing but Gaussian PDF. So that is substituted here in the second term. And then you get log, and then in the argument of the log, you have this exponential sitting. So if you simplify, you get two terms, one, which is here, which actually contains beta, and the second term, which doesn't contain beta, right? So if you are maximizing, you can safely ignore the second term, and it is only the first term that matters, and there is a negative sign sitting here, right? So this argmax becomes argmin over this summation. So you can see quite easily, right, that the ML estimate for beta is what we actually did already in least squares regression, right? So least squares regression was doing ML estimation under a specific generative model, right? Now, the reason why sometimes these type of insights can be helpful is if you look at the data, right, and you see that, there is just no way Gaussian distribution would have generated this data, then doing least squares regression on that data wouldn't just make much sense, right? So you sort of know when to apply each algorithm. And let me tell this more concretely again. So since Gaussian is not heavy-tailed, right, we are essentially assuming that your residual errors are small, right, or your errors are coming from a Gaussian distribution. That's sort of the exact model for which least squares, right, corresponds to the ML estimator. Now, what if a few training points exhibit large errors, right? We call them outliers. In that case, let's see if let me actually draw and see if least squares would still make sense, right? Let's say you had data which is something like this. Now, if you do least squares, you might get, for example, this line, right? It's pretty accurate, right? Pretty meaningful, at least I would say. And then what if you have again this data, and then you have a couple of outliers here, right? Maybe let's just put only 2 of them. So what you are going to get then is something like this, because in least squares, right, you are assuming that large errors won't occur, right? Because that is the generative model under which it makes sense. So if you now, let's say if you have outliers, right, is that a hopeless case? Obviously not. I mean, you can fix this simply by choosing a distribution that describes your data more accurately, right? So in this case, it would be choosing a distribution that allows larger errors, right, to occur. And one possibility is a Laplace distribution whose PDF has this form. It is a heavy-tailed distribution, right, for which larger values can also occur, which means large errors can also occur. And if you find the ML estimate in this case, it actually reduces to this form, which means this model where your underlying assumption is Laplace, right? Your loss function choice would be just the absolute loss, or L1 loss, right? We chose L2 loss before, so this is what we also called L1 loss, right? So if you have now large errors or outliers, this is the reason why you use absolute value loss, okay? All right. So with that quick note, let's actually proceed now to the map case, right? A map estimate or beta map for a similar example, right? So a natural question to ask is, are there similar connections between map and the loss function, right? We sort of connected the ML estimate with the squared loss and then with the L1 loss. So can we do something similar in the Bayesian setting as well? And the answer is yes. It leads to the Bayesian linear regression or regularized linear regression. Again, if you have been exposed to machine learning more from the algorithmic side, I think this discussion would be of interest to you. As before, we consider a Gaussian model, right? Y conditioned on xi is Gaussian with mean beta transpose x and variance sigma squared, right? Remember, this is nothing but y is, or let's say I should say yi, beta transpose xi plus a Gaussian term, right? Let's assume Gaussian prior, right? We put a Gaussian prior on the parameters beta, right, which is this. I mean, this is equivalent because we are in the variance, right? We have an identity matrix. This is equivalent to saying that beta i's are IID, and each of those beta i's is normal distributed, Gaussian distributed with mean zero, variance sigma squared. Now, the map estimate, right, is just maximization over the posterior. So let's see what that does in this specific case. I'm not going to write all this, but I'll just go through the steps which are already written one by one. So we have a posterior here. Really so we have already played with this term in the previous example, right? So this is the new term. This is a term that doesn't contain beta, so that can be safely ignored. So ignoring this, these are the two terms that we get, right? Now, this is nothing but the log likelihood that we already had, right? This gave us the least squared regression. This is the new term. If you simplify this, right, this term actually gives you this norm squared term. So you get lambda from this. And this term is also called regularization term, where lambda is the regularization parameter, right? And this is called regularized regression because of the presence of this term. And by the way, this regularization, or the general idea of regularization, is not limited to regression. You have regularization in neural networks and so on. And there is a specific role it plays. You can think of this as some type of a soft model selection in the following way, right? So if you look at this term with let's say a large lambda, what is it trying to do? It is trying to force beta, right, this vector, towards the all zero vector, right? And what it is doing is, if you have a large and a complicated hypothesis class, it is pulling data from higher order classes towards simpler classes. And this is the reason why regularization avoids overfitting. So this is the sort of connection between Bayesian, then regularization term, and overfitting. Okay. All right. So I'm left with only one very quick concept that I wanted to cover before we conclude this. So whenever you hear linear regression, right, it is very easy to dismiss that by saying, yeah, okay, it is linear regression. Our data is often more complicated, which is of course true to a large extent. So we cannot apply linear regression. So what I'm now going to show is that the concept that we introduced until now, right, the linear regression, is actually linear in a very specific sense. And for those attendees who haven't been exposed to this, that linear regression doesn't necessarily mean we are limited to the linear class. Okay, so let me explain that in a little bit more detail. So let's consider a simple case where we have a training example of the following form. You have input X, output Y. You have a single input X, let's say a single feature, right? We can always define hypothesis function as the mth order polynomial of X, right? So this is something I can define. Now, the thing to note here is that this function is linear in beta. It is linear in the parameters that we are learning and non-linear in X. So there is a distinction here. It is linear in beta and it is non-linear in X, right? However, for whatever we have developed until now, it is just the linearity in terms of beta that really matters, right? And the reason that statement is true is because of this idea of feature augmentation or basis expansion, right? Even if you had original features, let's say some x1, x2, x3, you can define nonlinear functions or new features from those existing features. Okay, and that is called feature augmentation or basis expansion. Let me show that through an example before we wrap up. Okay, so here we had, let's say, three features, x1, x2, x3, right? So you can come up with as many new features as you want. I mean, you could add a x1 squared, x2 squared, x1, x2, and things of that sort. You could create a much larger vector. This is called feature augmentation. And then you could potentially apply linear regression. You could have, say, beta 0, beta 1, beta 2, and so on, right? So a coefficient corresponding to each new feature, right? So what you are really doing here, right, that you are embedding a lower dimensional vector into a high dimensional space, and you're doing it in such a way that it facilitates linear processing, right? Now, doing this, like looking at the data, I just don't know, right, how to augment features. I mean, it's very difficult if your data set is very complicated. Now, this is where something like a neural network is so advantageous, because you don't have to artificially design these features or augment these features. So this feature learning is sort of done automatically in a neural network, right? So for those of you who have already gone through this, just think about it, and it will start making sense, right? Why this type of sort of a feature augmentation is going on automatically. All right, so I think we are almost there in terms of time. So let's quickly summarize our third lecture. So this was, as I said before, first of the two lectures on statistical estimation, connections to learning. And in this lecture, particularly, we focused on regression problem, right? We interpreted least squares regression as a maximum likelihood problem. We then also interpreted regularized linear regression as a map estimator. We also very quickly looked at polynomial regression, where the idea was to convey that, right, I mean, linear regression may not be as simple as it first seems, right? You can apply that idea also for polynomial regression. Okay, so in the second lecture of the day, lecture 4, right, we will be looking at similar ideas, but we'll be doing that for the classification problem. Okay. So today we won't be having a long case study, right? On the other 3 days, we have case studies from communications. And the reason is that the idea, right, or the reason for having these lectures on statistical estimation was to sort of bridge and also to convey that whatever tools we are already using, right, for wireless or communication system design in general are pretty much the same tools, right, that form the foundation of this area as well. Right, so that was sort of the bridge that we wanted to create on day 2. All right, so with that, I think I'll conclude now, and I will see you guys in the next lecture. Thank you so much for your attention.